This is the video for Accelerated Geometry on Section 16-1 on Properties of Logarithms. The essential question that we should be able to answer by the end of this video is how do you use properties to simplify logarithmic expressions? This first slide we're going to need to probably make note cards on so that we can memorize these properties, because if you don't know these properties, you're not going to be able to simplify the problems. Our first property is the product property, which just states that if you have the log of two numbers being multiplied together, you can break it up and have the log of the first number plus the log of the second number. So for example, if I said log of some base of 6, I can rewrite that because I know 6 is just 2 times 3. I can rewrite that as the log of that same base of 2 plus the log of that same base of 3, and vice versa. If I have the log of some base of 2 plus the log of some base of 3, then I can multiply 2 times 3 and rewrite it as just the log of that base of 6. The quotient property says if I'm dividing two numbers, then I can break them apart and have subtraction. Or if I see subtraction, then I can write them together as 1 being divided. So, for example, if we have the log of some base of 25 over 3, then I can rewrite that as the log of that same base of 25 minus the log of that same base of 3, and vice versa. Power property, if I'm taking the log of some number being raised to the power, I can just take that power and bring it out front and multiply it through that log. So for example, if I have the log of some base of 3 to the 5th, then I can say that that's equal to 5 times the log of that same base of 3. Inverse property is what it's saying is if you're taking the log of some base of a number being raised to an exponent, as long as this base of the log and the base of that exponent are the same number, then whatever your exponent is, that's going to be your answer. So for example, if I have the log of 2 to the 3rd, then that's just going to equal 3 because both these bases are 2. And if I have a number being raised to the log and the base of the log is the same as the base of the exponent, then again, whatever you're taking the log of is just going to be your answer. So if I had 4 log base 4 of 2, then that's just going to equal 2. Our change of base formula comes in handy when we're not looking at the log of base 10, because remember that if it's a log base 10, then all we see is the log, say like log of 4. We know that that is log base 10 of 4. However, if we're not looking at a log base 10 and our base is something other than 10, then we can use this formula, the log of x over the log of the base, to use our calculators to get an approximated answer. So, for example, if I have the log of 3 of 5, in my calculator I can type the log of 5 divided by the log of 3. So go ahead and pause the video and make sure you know how to use your calculator for the change of base, and pause it, try it, and then come back and see if you get the same answer as I do. A rounded answer should be about 1.465. Okay, let's try these properties and put them in use. First set of examples says to write each expression as a single logarithm. Notice it does not say evaluate, so our answer is not going to be a numerical answer. First thing I notice here is the subtraction, which leads me to our quotient property, which says that I can rewrite this as the log of the base, which in this case they're both base 3, of 10 over 5. Well, 10 over 5 can be reduced, so our final answer would just be log base 3 of 2. On example 2, we first have an addition here, which goes back to the product property, which says that I can take these two and multiply them. So I have the log of the base, which in this case is b, and if I multiply those, I just get uv minus the log b of uv. Subtraction is the quotient rule. So that tells me that I can rewrite that as log base b of uv divided by uv. Anything over itself is just 1, so our single logarithm here be the log base b of 1. Example 3, now we have subtraction first, so that means I'm going to take this 4x and the 3y, and I can rewrite it as a quotient. So that's going to be the log base b of 4x over 3y plus the log base b of y. Addition means to multiply, so I'm going to multiply this fraction times y. So that's just going to give me the log base b of 4x y over 3y. Then the y's are going to cancel. So my final answer would be the log base b of 4x over 3. Example 4, this is going to use our power property that says if I see a number in front that's being multiplied times the log, I can really take it and write it as the exponent. So first thing I'm going to do is take this 2 and write it as the exponent for 2a, and this 1/3 and write it as the exponent to b. So that's going to give me the log base z of 2a squared minus the log base z of b to the 1/3 plus the log base z of bc. Now we have subtraction, so I can write this as a division, but before I do that, I'm going to go ahead and carry that squared through. So this is really just going to be the log base z of 4a squared minus the log base z of b to the 1/3 plus the log base z of bc. So now I can divide these. So that's going to give me the log base z of 4a squared over b to the 1/3 plus the log z of bc. Addition means to multiply, so that's going to give me the log base z of 4a squared bc all over b to the 1/3. Now we have the b up top and the b on the bottom, so this is really b to the first. So b to the first minus b to the 1/3 is b to the 2/3. So my final answer is just log base z of 4a squared b to the 2/3 z. Next set of examples says to evaluate without using the change of base formulas, which means we really want to be focusing on our inverse properties. So we have the log base 2 of 8. So I'm going to think to myself, 8 is 2 to what power? Because I can rewrite that as log base 2 of 2 to the third, because 2 to the third is 8. Now I can use my inverse property that says the log base b of b to the x. I'm going to write it right here. So the log base b of b to the x is just equal to x. So since this base and this base are the same number, this is just going to equal 3. On number 6, we're going to ask ourselves, 16 is 4 to what power? And that's to the second. So I can rewrite this as log base 4 of 4 squared. And since these are the same number, that's just going to equal 2. Number 7, we have log base 5 of 25 to the fourth. So I'm going to ask myself, 25 is really 5 to what power, which is squared. So this is really log base 5 of 5 squared to the fourth, which this right here, exponent to an exponent, says to multiply. So that's really log base 5 of 5 to the 8th. And now since you have log base b of b to the 8th, then it's just going to be 8. Number 8 is similar to that. 27 is just 3 to the third. So I'm going to rewrite that as the log base 3 of 3 to the third to the 100. So that's really just log base 3 of 3 to the 300. And I guess I don't need these parentheses anymore. And now my answer is just 300. This is using the other property on example 9 that we have in our inverse rules that says that if you have a number raised to the log of a number of x, that's just going to equal x. So as long as the base of the exponent and the base of the log are the same, then your answer is just going to be whatever you're taking the log of. So for example, we have 3 raised to the log base 3. So since this base of the exponent is 3, the base of the log is 3, I know that this first part is just equal to 4. And then 25 is just 5 squared, so that's plus the log of 5 squared. So that's using the other one that we just did. So since it's log base b of b to the x, that's just going to be 2. And 4 plus 2 is 6. One more. 32 can be rewritten as 2 to the 5th. So this is really the log base 2 of 2 to the 5th minus 5 log, minus 5 to the log base 5 of 3. So this first one's just going to equal 5. The second one's just going to equal 3. And then 5 minus 3 is 2. Next two examples says to evaluate using the change of base formula, which means we need our calculators. So our change of base formula says that the log b of x is equal to the log of x divided by the log of b. So in this case, in my calculator, I'm going to type the log of 15 divided by the log of 12. And I should get 1.0898. On example 12, In my calculator, I would type the log of 56 divided by the log of 1/4, and I should get the decimal of about negative 2.9037. And the last thing that we're going to be doing in this section is finding the inverse of logs. So as we remember from earlier, to find the inverse, the first thing we do is switch our x and our y. So this is really just y equals the log base 4 of 3x. So I'm going to switch the x and the y. So that's going to become x equals the log base 4 of 3y. And since there's no addition, subtraction, multiplication, or anything going on, now I can just use our rule to convert from log to exponential. So our base is 4, so that's going to give me 4. The exponent is x, has to equal 3y. So all I did from this step to this step is convert from the log form to the exponential form. Then the last step was the opposite of multiplying by 3, that's dividing by 3. So I get 4 to the x divided by 3 equals y. So our final answer would be that the inverse of f of x is equal to 4 to the x over 3. Let's try another one. So this is really y equals the log of 3y minus 5. I'm sorry. This would be an x right now. So now I'm going to switch them. That gives me x equals the log of 3y minus 5. Opposite of subtraction is adding, so I'm going to add 5 to the other side. So that gives me x plus 5 equals the log of 3y. So now I can take it from log form to exponential. Remember that if there's no base here, the base is 10. So this is really 10 to the x plus 5 equals 3y. And then we're going to divide by 3. So we have 10 to the x plus 5 over 3 equals the new y. But our final answer, we have to denote it as the inverse. So we're going to have f inverse of x is equal to 10 to the x plus 5 all over 3. And I'm going to rewrite this so that you can also remember. Please make sure that if it's an exponent that it looks like an exponent. One more. So first thing we're going to do is rewrite this. So this is going to be y equals the log base 1/2 of 2x minus 5 plus 6. Switch our x and our y. The opposite of addition is subtraction, so I'm going to subtract 6 to the other side. And now since I just have a single log on the right side here, I can take it from log form to exponential form. So that's going to give me 1/2 to the x minus 6 equals 2y minus 5. Opposite of subtracting 5 is adding 5. So that's going to give me 1/2 to the x minus 6 plus 5 equals 2y. And then lastly, divide by 2. So that's going to give me 1/2 to the x minus 6 plus 5 all over 2 is equal to y. So our final answer on this problem would be that f inverse of x equals 1/2 to the x minus 6 plus 5 all over 2.